Hi, my name is Karen Carter, and I elected to present a topic out of the Hacking, the Art of Exploitation book, Chapter 4, which is on networking. Topics covered in this chapter, and this is not an all-inclusive list, are the OSI model, what sockets are and how they function, network byte order, which I learned about while doing the exploit exercises. It is Indianness. Remember Big Indian or Little Indian? It also covered TCP/IP headers, network sniffing, and different types of network hacking attacks. There was a whole lot of C code I had to decipher through. As you know, we were instructed to pick something out of this chapter that caught our interest and give our 1-hour presentation. Well, the author's words, and I quote, "Since IPv4 is most common, IP will always refer to IPv4 in this book." Then later on in the chapter, he makes a comment when discussing the ping of death. He states an ICMP echo message of this gargantuan size became affectionately known as the ping of death. It was a very simple hack exploiting a vulnerability that existed because no one ever considered the possibility. It should be easy for you to write a program using libnet, and libnet is a generic networking API that provides access to several protocols. This is something we learned in the chapter. He states we can use a libnet that can perform this attack, however it won't be useful in the real world, and this is because modern systems are all patched against this vulnerability. However, history tends to repeat itself. Even though oversized ICMP packets won't crash computers anymore, new technologies sometimes suffer from similar problems. It was this last statement, new technologies suffer from similar problems. That is when it hit me. IPv6 is a newer technology and has a totally different structure from IPv4. And it also appears way more complicated in my eyes. I thought, I bet there are attacks out there right now on it. I know when I lock down my network devices using the DISA-STIGs, there are IPv6 vulnerabilities listed. I did some research on the internet, and guess what? There is a lot of information out there on hacking IPv6 systems. That is when I decided to come out of my comfort zone in IPv4 and dive into the unknown dark world of IPv6. There is a benefit in learning it for me too. I am a network engineer for the Department of Defense, and IPv6 is on the horizon for me. For the past 5 to 8 years, I have only been able to purchase network equipment that is IPv6 compatible, and they are starting to send us to training on IPv6. I have heard IPv6 is a protocol that will never be used. We've been hearing about it for the last decade but haven't seen it evolve. There is a joke. IPv6 walks into a bar and nobody talks to him. Well, guess what? In perfect timing for me, June 6th of this year was IPv6 World Launch Day. IPv6 is here to stay, and it is being used. The 4 biggest websites, Google, Facebook, YouTube, and Yahoo, have all permanently enabled IPv6. I am now going to show you a short video clip. Leslie Daigle, the Internet Society Chief Internet Technology Officer, summarizes the event that happened and thanks all the participants for their part in this great step in the evolution of the Internet. Please excuse the echo, and you may need to turn your system up a bit.
My name is Leslie Daigle, and I'm the Chief Internet Technology Officer for the Internet Society. And I'd like to tell you about the World IPv6 launch, which is happening on June 6th of 2012. This is an event that the Internet Society is quite pleased to be hosting as a collaboration between a number of content providers, service providers, and hardware manufacturers around the globe. It is the day on which all of these organizations that are participating will turn on commercial-grade IPv6 services. So the participating service providers, such as Time Warner Cable, Comcast, AT&T in the US, Access for All in Europe, and KDDI, are turning on IPv6 access to their existing customers and new customers. Top Alexa-ranked content providers, such as Google, Facebook, and Yahoo, are also turning on IPv6 on their main websites for good as of June 6th. This is a really important step for the Internet because at this point, the Internet that we know today runs on IPv4 addresses, but there are only 4 billion addresses in the IPv4 address space. Given that that's fewer than there are people on the face of the planet, we need to move on from there. And IPv6 is that next step forward. So what does this mean for you as a user? Well, if we do it right, you won't notice a thing. It will just smoothly be a transition from the internet that you know today, that's flexible, open, upon which you can run whatever new services and software that you have and are interested in. But if things don't move smoothly, if the progress towards IPv6 isn't moved along quickly at this point, you will find that the coping mechanisms to deal with a runout of IPv4 addresses are going to cause problems for some of your games that won't run as smoothly, some access to some websites will be more difficult or blocked, and in general it just won't be the internet that you know and love today. So what can you do about it? Well, you can certainly look at the website for this activity, worldipv6launch.org, and take a look at who's participating. See if your access provider is listed among our participants, and if not, give them a ring. Ask them when they're planning to offer you IPv6 service. And certainly we look forward to seeing the IPv6 internet after June 6th, and hope you'll be there too.
So as you can see, IPv6 is here to stay, and I bet the comment she made about problems with some of the gaming websites probably caught your attention. I'm sure the global inauguration of IPv6 opened up a whole new playground for black hat hackers as they feed on challenges and conquests. This video presentation, if you haven't already figured it out, is on hacking IPv6. As a part of the assignment, I am required to give you an exercise and then provide the answer to you. My approach to this is I will be giving you challenge questions throughout my presentation that will require some hands-on and some cranial work, and then I will provide the answers at the end, so you need to pay attention. I will be demonstrating a man-in-the-middle attack and a Smurf denial of service attack using IPv6. So why IPv6? As you heard in the video, there are only 4 billion IPv4 addresses, less than the amount of people in this world. Granted, we have private IP addresses, network address translation, and subnetting to help with the depletion of these addresses, but even that wasn't enough. Network World reported on February 1, 2011 that the IANA had assigned 2 of the remaining blocks of IPv4 addresses to AppNIC. At the time, experts said it would take anywhere from 3 to 7 months for the registries to distribute the remaining IPv4 addresses to carriers. Now, mind you, this was last year. We are now out of IPv4 addresses. Once the registries handed out all the IP4 addresses, network operators must either deploy complex, expensive network address translation technologies to share IPv4 addresses among multiple users, or adopt the next generation of the IP protocol called IPv6. IPv6 has a 128-bit address, or 2 to the 128th, which will give us 340 trillion addresses, or 340 undezillion. I think it will take us a while to exhaust this many IP addresses. Before you perform a network hack into any system, you need to have a knowledge of the network protocols you are using to perform that hack. We are now going to get into the nuts and bolts of IPv6. You should be familiar with the basics of the OSI model, networking, and the IPv4 protocol. I am first going to talk about the difference between the IPv4 header and IPv6 header format. The IPv4 header contains 12 fields. Following those fields is an option field of variable length as outlined in red, and finally a data portion, which is usually the transport layer packet. The basic IPv4 header has a size of 20 octets. The options increase the size of the total IP header. Of these 12 header fields, 6 fields are removed in IPv6, and these are outlined in blue. The main reason to remove these fields are the fragmentation is now handled differently and does not need the fields in the basic IP header. Because IPv6 routers do not handle fragmentation as in IPv4, the processing issues caused by routers handling fragmentation are eliminated in IPv6. The removal of a checksum at the IP layer is because most link layer technologies already do a checksum and error control, and because of the reliability of the link layer is very good, IP header checksum was considered unnecessary and not very useful. However, this removal forces the upper layer optional checksums like UDP to become mandatory. The options field is not handled by an extension header chain. The majority of the other fields were either not changed or only changed slightly. The IPv6 header now has 40 octets instead of 20 octets as in IPv4. It has a smaller number of fields, and the header is 64 bits aligned to enable fast processing by our current processors. Address fields are 4 times larger than an IPv4. The IPv6 header contains the following fields. The version field is a 4-bit field as in IPv4. It contains the number 6 instead of the number 4. The traffic class field is an 8-bit field and is similar to the type of service field in IPv4. It tags the packet with the traffic class that can be used in differentiated services. These functionalities are the same on IPv6 and on IPv4. The flow label field is a completely new field. It has a length of 20 bits. It is entitled to tag a flow for the IP packets. The payload length is similar to the total length of IPv4. The value of the next header field determines the type of information following the basic IPv6 header. It can be a transport layer packet such as TCP or UDP, or it can be an extension header. The next header field is similar to the protocol field of IPv4. The hop limit field specifies the maximum number of hops an IP packet can traverse. Each hop or router will decrease this field by 1. Since there is no checksum in the IPv6 header, this can be quickly achieved by the router without the need to recompute the checksum, which costs processing time on IPv4 routers. The source address field is 16 octets or 128 bits. It identifies the source of the packet. The destination address field is also 16 octets or 128 bits and identifies the destination of the packet. The following 8 fields are the extension headers, if any, and then the data portion of the packet. The number of extension headers is not fixed, so the total length of the extension header chain is variable. We are now going to talk about the IPv6 IP address, but first, let's take a look at the difference of the structure between the two. The first obvious difference is the size of the address. IPv4 is 32 bits, and IPv6 is 4 times that, at 128 bits. IPv4 addresses convert from binary to decimal, whereas IPv6 addresses convert from binary to hexadecimal. We are now going to look at the structure of an IPv6 address. IPv6 addresses are represented as a series of 16-bit hexadecimal fields separated by colons. Like an IPv4 address, IPv6 addresses are divided by a network and a host address. A mask of /64 means the first 64 bits are the network address and the remaining 64 bits are the host. This mask will be used the majority of the time. Can you imagine having to ping this address? There is a shortcut you can use and it helps a little bit. The leading zeros in a field are optional, so that 09C0 equals 9C0 and 4 zeros equals 1 0. If you have zeros in your address, you can take them out and replace them with the double colon. However, you can only use a double colon once in an IPv6 address. An address parser is able to identify the number of missing zeros by putting the two parts apart and filling 0 in the place of the double colon until the 128 bits is complete. But if 2 double colons are placed in the address, then there is no way to identify the size of each block of zeros. So once again, only one set of double colons is possible in a valid IPv6 address. The use of the double colon technique makes many addresses very small, for example the one you see here. We've come to our first challenge question. Pause the video and shorten the following address using the double colon technique. In a URL, the colon is already used to place an optional port number, as you can see in this URL. A URL parser must then differentiate between the colon of a port number and the colon inside an IPv6 address, which is impossible because of the compression technique. In order to identify the IPv6 address while still keeping the colon, the address must be enclosed between brackets, as shown here. In Microsoft Windows operating systems, IPv4 addresses are valid location identifiers and Uniform Naming Convention path names, also known as UNC path names. However, the colon is an illegal character in a UNC path name. Therefore, the use of an IPv6 address is also illegal in UNC names. For this reason, Microsoft implemented a transcription algorithm to represent an IPv6 address in the form of a domain name that can be used in UNC paths. For this purpose, Microsoft registered and reserved the second-level domain IPv6-literal.net on the Internet. IPv6 addresses are transcribed as a host name or subdomain name within this namespace as shown here. IPv6 addresses are classified by the primary addressing and routing methodologies common in networking. Those are unicast, anycast, and multicast addressing. A unicast address identifies a single network interface. The Internet Protocol delivers packets sent to a unicast address to that specific interface. An anycast address is assigned to a group of interfaces, usually belonging to different nodes. A packet sent to an anycast address is delivered to just one of the member interfaces, typically the nearest host, according to the routing protocol's definition of distance. A multicast address is also used by multiple hosts, which acquire the multicast address destination by participating in the multicast distribution protocol among the network routers. A packet that is sent to a multicast address is delivered to all interfaces that have joined the corresponding multicast group. IPv6 does not implement broadcast addressing. Broadcast traditional role is replaced by multicast addressing to the all nodes link local multicast group of FF02:1. However, the use of the all nodes group is not recommended, and most IPv6 protocols use a dedicated link local multicast group to avoid disturbing every node on the network. Multicast plays a huge role in IPv6. The multicast addresses FF00 with the /8 subnet mask are reserved and should not be assigned to any multicast group. The IANA manages these address reservations. I have listed some of these reservations, and you are probably wondering what link local is. Well, you are about to find out. Guess what? IP gives us two IP addresses, a global Internet routable IP and a link local IP, which is only good on the local network segment. An IPv6 global IP address is a unicast address and is routable on the Internet. If you want to see if your Internet service provider is offering IP services, you can enable IPv6 on your Windows or Linux system, do an ipconfig or ifconfig to see if you have a global IPv6 address. Verizon Wireless is my ISP, and as you can see, they are using IPv6 on their network. I found an interesting white paper on how IPv6 addresses are being allocated and distributed. I've included the link at the bottom of the slide. The link local address is like the private IP address provided in IPv4, the 192.168 or the 172.16, in the sense that it is not an Internet routable IP. And unlike IPv4, it is not obtained from a reserved IP address space. The difference between IPv4 and IPv6 with this address is that every device is given a link local address. The goal of the link local address is connectivity on the local network segment. So, how does the system come up with this address? All link local addresses start with FE80, which is reserved by the IETF. The first 64 bits are FE80 followed by 12 zeros. The second 64 bits use the MAC address of the system. There's a problem with this though, and that takes us to challenge question number 2. What is the problem with adding the MAC address to the last 64 bits of a link local address? We're going to get lucky on this one because I need to give you the answer before I continue. And the answer is the MAC address is only 48 bits and we need 64 bits. So how do we get the additional 12 bits added to the host portion of our link local address? Once we add the 12 bits, we will have a modified EUI 64-bit address. It is a two-step process. In the first step, the system injects FFFE into the middle of the MAC address. For instance, take the MAC address in my computer. The FFFE will be inserted right after the 6B. Why FFFE? This is a reserved value which equipment manufacturers cannot include in a real EUI-64 address. In other words, any EUI-64 address having FFFE immediately following its OUI portion can be recognized as having been generated from an EUI-48 or MAC address. The second step is to invert the universal or local flag bit, which is the 7th bit in the MAC portion of the address. Globally unique addresses assigned by the IEEE originally have this bit set to 0, indicating global uniqueness. Likewise, locally created addresses, such as those used for virtual interfaces or a MAC address manually configured by an administrator, will have this bit set to 1. The UL bit is inverted when using an EUI64 address as an IPv6 interface ID. The 2 steps have been performed on my MAC address, and this is now my link local address for my laptop. And now on to challenge question number 3. Given this link local address, what is the MAC address? Microsoft has to be different. It throws its own twist on an international standard. Again, it decided it didn't want IPv6 to generate its own link local address, but instead it would do it for it, using its own randomizer. The reasoning behind this is the chance of duplicating the link local address is very small. Therefore, computers running Windows Vista or Windows Server 2008, or in my case Windows 2007, they do not wait for dynamic address discovery to complete before sending router solicitation messages using their derived link local addresses. This is known as optimistic dynamic address discovery, and these are performed in parallel to save time during the interface initialization process. I have provided the command at the top of the screen to disable this, which I did on my system. ARP uses broadcast, and IPv6 doesn't support broadcast, so how are we going to find our neighbors? We are going to use the Neighbor Discovery Protocol. RFC 2461, the standards track for neighbor discovery for IP version 6 states, nodes, which are hosts and routers, use neighbor discovery to determine the link layer addresses for neighbors known to reside on attached links and to quickly purge cached values that become invalid. Hosts also use neighbor discovery to find neighboring routers that are willing to forward packets on their behalf. Neighbor discovery is a process that enables the following functions. It determines the link layer address of a neighbor on the same link, it finds neighbor routers, and it keeps track of neighbors. How does it achieve this? Through the ICMP protocol with multicast addresses. The Network Discovery Protocol defines the following 5 ICMP version 6 packet types: router solicitation, router advertisement, neighbor solicitation, neighbor advertisement, and redirect. I will be showing you neighbor solicitation and neighbor advertisement. A solicited node multicast address is an IPv6 multicast address valid within the local link, for example an Ethernet segment. Every IPv6 host will have at least one such address per interface. Solicited node multicast addresses are used in the Neighbor Discovery Protocol for obtaining the Layer 2 link layer addresses of other nodes. Any node must join the multicast group corresponding to each of its unicast and anycast addresses. The solicited node address is composed of the following, and that's the FF02 address you see at the bottom. And this prefix is concatenated by the rightmost 24 bits of the corresponding unicast or anycast address. And as you can see, I have 2 examples. As an FF02 address, a solicited node multicast address has the scope of the link local address. Solicited node addresses are used for neighbor solicitation messages where another node needs the link layer address of an IPv6 address in order to send the right frame on the link layer. The other node takes the rightmost 24 bits of the IPv6 address of the correspondent node and sends a neighbor solicitation message to the multicast group on the link local. The corresponding node will respond with its link layer address. Solicited node multicast addresses are used with IPv6 neighbor discovery to provide the same function as the address resolution protocol in IPv4. ARP uses broadcast to send an ARP request to the broadcast address 255.255.255.255, which is received by all stations on the local link. Although only one station, the one being queried, would need to respond, the other stations still have to process and discard the request. This interruption can cause problems on networks if the amount of broadcast traffic becomes excessive. Devices such as embedded print servers might not be able to cope with the amount of traffic they are processing and fail to operate in a timely manner. Because a solicited node multicast address is a function of the last 24 bits of an IPv6 unicast or anycast address, the number of hosts that are subscribed to each solicited node multicast address is very small. This number would typically be 1, but there could be a few because the mapping function is not a one-to-one mapping. This means that a host should not need to be interrupted as often to service neighbor solicitation requests compared to ARP and IPv4. So how does the Neighbor Discovery Protocol work? Before I get into the nuts and bolts of neighbor solicitation and neighbor advertisement, I have another challenge question for you. At what layer of the OSI model does the Neighbor Discovery Protocol do her job? I am now going to explain neighbor solicitation and neighbor advertisement using the Neighbor Discovery Protocol, and then I will give a demonstration of it. This example shows the determination of the link layer address of a neighbor called neighbor solicitation. This function is similar to ARP and IPv4. As a matter of efficiency, the request also sends the link layer address of the source node. The ICMP message of type 135, identified as neighbor solicitation, is sent on the link. The source address is the IPv6 address of the source node, if known. The destination address is the solicited node multicast address corresponding to the IPv6 address of the destination node. The message also includes the link layer address of the source node so that the destination node will be able to use it right away. The destination node responds with an ICMP message of type 136, identified as neighbor advertisement on the link. The source address of the responding message is the IPv6 address of the destination node, and the destination address is the IPv6 address of the source node because it is the answer. The data portion includes the link layer address of the destination node, which is actually redundant with the link layer address included in the frame. After receiving the answer, the source node and the destination node are able to communicate on the link because the link layer addresses are known to both. The neighbor solicitation process is also used to verify the reachability of a neighbor. In that case, the destination address is not the multicast address, but the unicast address of a neighbor. Neighbor advertisements can be sent when there are changes in the link layer addresses. In that case, the source of the advertisement sends a message to the all node multicast address. Did that previous slide confuse you? It did me. Here is Karen's version of what I just explained. Computer A sends a neighbor solicitation request, which is ICMP type 135, and in this request he is asking for whoever has this link local address, I need your layer 2 address. Computer B says, hey, I have that link local address, and responds with the neighbor advertisement, which is ICMP type 136. In this response, he includes his layer 2 address and also asks Computer A for his information. Once they get it, the two computers can communicate. We are now going to see the Neighbor Discovery Protocol in action. I am now going to ping a link local address on my network. In Windows, it's ping-6. If you look over to the right here, once I start pinging, we should see the neighbor solicitation and neighbor advertisement come through. There they are. And let me go ahead and stop this and we'll take a look at it. We first see the solicited node multicast address FF02::1 with the last 24 bits of the destination's link local address appended to it. Next, we see the neighbor solicitation from my laptop. The last 4 of my link local address is 17F8. Now let's take a look at the packet. Here we can see the neighbor solicitation ICMP type of 135, and we also see our source and the destination. We are now going to look at the neighbor advertisement. As you can see, this is coming from the destination machine. We are now going to look at the ICMP packet. And here we can see the ICMP type of 136, which is the neighbor advertisement, and it also has the source and the destination, link local address, and MAC address. Now these two systems can communicate. A command that is similar to the ARP-A command in IPv4 is the show neighbors command for IPv6. In Windows, the command is netshow interface IPv6 show neighbors. Get a lot of information. There's our multicast addresses along with our global addresses. And up here we see the two networks, the two laptops that are on my local network, I should say. They're both saying stale. The only reason this is because they haven't received a neighbor solicitation in 30 seconds or less. So I'm going to go ahead and send them one. I'm going to ping the Linux box that you see on the screen. I'm going to run the netshow command again. And here we see it's reachable. I'm going to go over to this box now and do a show neighbor command. In Linux, that command is IP-6 neighbor show. And here we're seeing the laptop that I am sitting at is reachable. Stateless node auto-configuration is a key feature of IPv6. It enables serverless basic configuration of the nodes and easy renumbering. Stateless auto-configuration uses the information in the router advertisement messages to configure the node. The prefix included in the router advertisement is used as the /64 prefix for the node address. The other 64 bits are obtained by the interface identifier, which in this case of Ethernet is a modified EUI64 format. Before I continue on with stateless auto configuration, I have another challenge question for you. Do you remember what the EUI64 format is and how we created a modified one? Now back to stateless auto configuration. Router advertisements are sent periodically. When a node boots, the node needs its address in the early stage of the boot process. The wait for the next router advertisement to get the information to configure its interfaces can be lengthy. Instead, a node sends a router solicitation message to the routers on the network to reply immediately with the router advertisement so that the node can immediately auto-configure. All the routers respond with the normal router advertisement message with the all nodes multicast address as the destination address. Renumbering of nodes is achieved by sending router advertisements. These messages contain both the old prefix and the new prefix. By decreasing the lifetime of the old prefix, this tells the nodes to use the new prefix while still keeping their current connections opened with the old prefix. During that period of time, nodes have two unicast addresses to use. When the old prefix is no longer usable, the router advertisements will include only the new prefix. If stateless auto configuration is not used, then other ways of renumbering should be used. Auto configuration greatly helps the renumbering process. Renumbering of a whole site also means that the routers need to be renumbered. A router renumbering protocol is defined for that purpose in RFC 2894, Router Renumbering for IPv6. Duplicate Address Detection, or DAD, uses neighbor solicitation to query if another node on the link has the same IPv6 address. It sends a neighbor solicitation packet to the solicited node multicast address of its own IPv6 address. The source address of this packet is the unspecified address, which you see as the double colons. If a node responds to that request, it means that the IPv6 address is used and the requesting node should not use that address. DAT is used during the auto configuration process in order to make sure that no one else is using the auto configuration address. DNS for IPv4 does not support IPv6 addresses. New records have been defined to support IPv6 addresses. The following records and new functions are defined. The quadruple A records, these are the IPv6 equivalent of the A record that implements the host name to IP address mapping. With quadruple A records, the IP address received is the IPv6 address. Inverse mapping, the IP address to host name, uses the pointer record as usual. The top-level domain for the IPv6 address is ip6.arpa. At the beginning of IPv6 DNS, the top-level domain was ip6.int. The example shows the IPv4 and IPv6 formats of the DNS records. The Dynamic Host Configuration Protocol is an updated version of DHCP for IPv4. It supports the addressing model of IPv6 and benefits from new IPv6 features. These features are: it enables more control than serverless, stateless auto configuration, can be used in a routerless environment using only servers, can also be used concurrently with stateless auto configuration, can be used for renumbering, and can be used for automatic domain name registration of hosts using dynamic DNS. The process for acquiring configuration data for a client is similar to that in IPv4, but with a few exceptions. Initially, the client must first detect the presence of routers on the link using neighbor discovery messages. If at least one router is found, then the client examines the router advertisements to determine if DHCP should be used. If the router advertisements enable use of DHCP on that link, or if no router is found, then the client starts a DHCP solicit phase to find a DHCP server. DHCP version 6 uses multicast for many messages. When the client sends a solicit message, it sends the message to the all DHCP agents multicast address with link local scope. Agents include both servers and relays. When a DHCP relay forwards a message, it can forward it to the all DHCP server's multicast address with site local scope. This means that a relay does not need to be configured with all the static addresses of the DHCP servers as in IPv4. If needed by policy, a relay can contain a static list of DHCP servers. Some servers can be configured to give global addresses using some policies, for example, more restrictive, do not give to printer, while others, or the same within a different context, can be configured to give site local addresses using a different policy, for example, more liberal, give to anyone. DHCP version 6 uses the following addresses. The FF02:1:2 is the all DHCP agents address, which is used by clients to communicate with the agents located on their local link and that are unknown. This address is of link local scope. The FF05:1:3 is the all DHCP server's address, which is used by relays or clients to communicate with site-wide servers that are unknown. This address is of site local scope. A node sending a message to that destination address should use a source address that will be reachable by the server for the answer. For example, a link local address cannot be used as a source address for this kind of message. Security inside IPv6 is achieved by IPsec protocols. IPsec is available in both IPv4 and IPv6, but it is mandatory in IPv6. IPsec has two separate headers that can be chained in the same IPv6 packet through extension headers. There are many related protocols for IPsec, such as the key management protocols. Authentication header provides integrity and authentication of the source. It also provides optional protection against replays. It protects the integrity of most of the IP header fields, but not all because some change over the path. It authenticates the source through a signature-based algorithm. The key difference between IPv4 and IPv6 related to security is the fact that IPsec is mandatory for IPv6. This means that all IP communications can be secured if there is enough keying infrastructure to do so on a large-scale basis. The other IPsec security header is the encapsulating security payload header. It provides confidentiality, authentication of the source, connectionless integrity of the inner packet, anti-airplay, and limited traffic flow confidentiality. I am now going to demonstrate two attacks on IPv6. The first one is sniffing and the man-in-the-middle attack, and the second one is a Smurf denial of service attack. Before I get into my demonstrations, I have one last challenge question for you. Which DNS record types were added for IPv6? Okay, we now have enough ammunition to proceed with our attacks. The first attack is a man-in-the-middle with a spoofed neighbor advertisement. A man-in-the-middle attack is a form of active eavesdropping in which the attacker makes independent connections with the victims and relays messages between them, making them believe that they are talking directly to each other over a private connection, when in fact the entire conversation is controlled by the attacker. The attacker must be able to intercept all messages going between the two victims. I will be using the Parasite6 script, which is from Van Houser's The Hacker's Choice Toolkit, which, by the way, this toolkit is installed on your Backtrack 5 machine. Now let me set the stage for you. We have our client who is going to FTP into our FTP server. Our client machine is a Windows 7 system, and the FTP server and the attacker systems are both Linux systems. On each system I have labeled it with its role and the last four of the link local address. I chose different operating systems so you can see the difference between the IPv6 commands between Windows and Linux. The first test is to send the ICMP version 6 echo request from the client to the FTP server, and in Windows this is the -6 command. Then we are going to take a look at the neighbor cache entry. To view our IPv6 neighbors in Windows, we use the netshow command. Here we see our multicast and our global addresses. And the 3076 is the FTP server that we just pinged, and it is reachable. And please take note that the physical address matches the last four of the link local address. I am now going to go over to the Linux box, the FTP server, and do a show IPv6 neighbor on it also. The command in Linux is IP-6 neighbor show. And as we can see, the FTP server and the client are talking. The next test is started by enabling IPv6 forwarding and utilizing the Parasite6 script on the attacker computer. The goal here is to perform a man-in-the-middle using spoofed neighbor advertisement. I will also open up a TCP dump session to show you traffic is being rerouted to the attacker. I am first going to enable IPv6 forwarding. Now I'm going to run the Parasite6 script. Okay, it's running and started. And now for my TCP dump session. Okay, it's ready and waiting. The attacker is ready and waiting for connections. He's sniffing the network. We will now go back to the client and ping the FTP server again. This time the attacker will intercept the packets coming from the client. And we can see the attacker is intercepting the packets from our client. Let's go back and look at the neighbor cache on the client again. Notice the FTP server's IPv6 address is attached to the attacker's MAC address. As you can see here, the IP address is 3F76, but the MAC address is that of our attacker, 3EF7. The test is continued by sniffing the FTP connection from the client to the FTP server. The goal is to intercept the username and password used to log in to the server. The attacker allows IPv6 forwarding and utilizes the Parasite6 script along with TCP dump. During the login process, the TCP dump in the attacker's computer captures all traffic from the client to the FTP server. This dump is written on the pcat file and is saved in the temp directory as ftp.pcap. In order to read the pcat file easily, we will use Wireshark. The client will now connect to the FTP server and log in with valid credentials. And as you can see, the entire time the attacker is sniffing the connection, and it is also logging the session to the ftp.pcap file, which we will now look at. I am on the attacker's computer, and I'm going to go into the temp directory. Here we see the ftp.pcap file that was created during the TCP dump session. In order to read this easily, I'm going to open up Wireshark and bring this file into it. There's a lot in there. I'm going to go ahead and sort on protocol, and we're looking for FTP, mainly usernames and passwords. And here we go. The username was Dan and his password. The man-in-the-middle attack was successful. My next attack is a denial of service, but first I have a joke for you. IPv4 networks are susceptible to Smurf attacks, where a packet is forged from a victim's address and then sent to the subnet broadcast of an IPv4 LAN segment. All hosts on that LAN segment receive that packet and send back an echo reply to the spoofed victim's address. This overloads the victim's IP address with lots of traffic and causes a denial of service. Because IPv6 does not use broadcast as a form of communication, it's assumed that these types of attacks are limited. However, IPv6 relies heavily on multicast, and these multicast addresses might be used for traffic amplification. An attacker on a subnet could try to send traffic to the link local all nodes multicast address, which is FF02::1, and the link local all routers multicast address, FF02::2. One example of using multicast to leverage an amplification attack is demonstrated with the Hacker's Choice IPv6 attack toolkit using the Smurf6 tool. The Smurf6 tool sends locally initiated ICMP version 6 echo request packets toward the multicast address FF02::1, and then the hosts on that LAN that are vulnerable to the attack generate ICMP version 6 echo response packets back to that source, which is the unknowing victim. The Smurf6 victim can be on the local subnet with an attacker or on a remote subnet. Our victim is going to be the FTP server, and it's on a local subnet. A denial of service attack is one of the simplest forms of a network attack. Instead of trying to steal information, a denial of service attack simply prevents access to a service or resource. The first thing we are going to do is ping from the client to the FTP server without the IPv6 tool running. I'm going to do a -T, which is a continuous ping. And as you can see, I do have some latency issues on my network. This is because I have two VNC servers running at the same time. However, you will see a major change when I run the IPv6 tool. Right now I am going to run the ifstat on the FTP server. ifstat is a tool that reports network interface bandwidth. And notice the numbers on the far right. These will change when I run the IPv6 tool, which I'm getting ready to do now. I am now going to run the IPv6 command on the attacker machine. The command is IPv6, the interface, and then the link local address of the victim. I am also going to run a TCP dump session so we can look at what's happening in a few minutes in Wireshark. Let's see what's happening on our machines over here. The pings are slowing down, and the ping times are getting bigger. The FTP server is now being flooded with oversized packets, which will eventually not let any new incoming packets through, thus your denial of service. We are now going to go in and look at the dos.pcat file in Wireshark to see exactly what was happening. We see here that the spoofed ICMP version 6 echo request from the FTP server is destined to the FF02:1 address, which is the multicast address for all nodes. All other computers on the network will reply to this request destined to the FTP server. Samuel Buchholz wrote an editorial in June of 2011 on how secure is IPv6. He states the massive internet transition from IPv4 to IPv6 is not without some risks to security. The biggest challenge CISOs will face is the blank state effect of a brand new internet protocol. After all, we've had decades to learn IPv4 inside and out. Now that we have a new protocol, we have to start over at the beginning. Will hackers exploit the IPv6 transition to create a new wave of attacks against businesses? He states yes and no. In theory, hackers could use a transitional period to exploit a weak user base knowledge of the new protocol, but remember, there is a learning curve here for black hats too. It's also important to note that IPv6 does come with better security options and requirements than its predecessor, which we learned in this demonstration. Listed are the 5 security issues that he foresees with the IPv6 transition, and that is poor implementation and misconfiguration, dual stack attacks, integration with DNSSEC and IPsec, device and application support, and protocol design, functions like mobility that haven't been tested. And here are the answers to your challenge questions. And this concludes my presentation. I hoped you learned as much about IPv6 as I did when I was making this video.